Hello, this is Alireza Aminlu from Nokia, Finland. I'm presenting my paper in Packet Video Workshop. Title is Extended Support for Subblock-based Affine Motion Compensation of VVC. So introduction. Versatile video coding, which is a video coding standard, is going to be finalized this year, and it shows roughly 50% bitrate reduction compared to the previous standard HEVC. It mainly targets natural video coding, but also targets coding new types of the video contents like immersive application related or VR related content. VVC has many coding tools I listed here, but I'm not going to all of details. The tool that we are studying about that in this paper is affine motion compensation. So affine motion compensation, in basic idea is that the motion vector and the location of for each pixel in the reference frame is found with this matrix-based mapping. So it's able to capture the rotation, resizing, deformation, shearing, different types of changes. Here in this figure, you see the reference blocks, reference pixel samples with a square, and circles are the samples which are predicted with affine motion model. This is accurate and sample-based motion model. But the affine motion model in VVC is a bit simplified version. First, the way that parameters are signaled is that instead of signaling 6 parameters, the motion vector for the top left, top right, and sometimes bottom left corner are signaled. But the most simplification is that it is block-based. So each block is divided, you see in the figure below, each block is divided to 4x4 sub-blocks, and motion vector is calculated for each sub-block based on affine parameter. Then normal motion compensation, translational motion compensation is applied for each sub-block. So the problem here is that there is discontinuity. You see that the sub-block boundaries has discontinuity. So the solution for this one in VVC is PRAF. PRAF is prediction refinement with optical flow. So as you see in this figure, the ideal sample location that with affine we are looking for that are these orange location, but because of this sub-block based affine motion compensation, we have these red ones. So with PRAF, it tries to estimate the values of these orange circles using this red circle. So it calculates the gradient of the content and then also calculate this motion vector refinement, this blue arrows, and then refines the predicted sub-block. So in total, this affine and PRAF together shows about 3 or 3.5% gain. But the problem is with large rotation. Large rotation may happen in different VR content. In top right, you see that there is a ERP in full resolution, and then the same ERP rotated in half resolution packed on the left side. So there is this kind of rotation. Or in this CMP, the figure on the bottom right corner, this is CMP representation of 360 data. So when one content goes outside, that I showed with this, let me show with the pointer, go outside, when one object goes outside from this side, then it will go and appear from the other side, but rotated 90 degrees. The other example is this video-based point cloud. In I will explain it later, but here you see that different objects in different frames are rotated, like this lady in this frame and this frame are rotated. So there is large rotation in some content. But the problem with the current block-based affine motion compensation in VVC is that it doesn't handle this large rotation. For example, in this example, let's say this is the current object in the current frame. It was, let's say it was like this in the previous frame. So with these motion vectors, theoretically it is possible to signal this 90-degree rotation. But when you apply the subblock-based affine motion compensation, the prediction block will be like this, which is completely useless. Or in the example below, when there is vertical flipping can be signaled with these motion vectors, but the affine motion compensation will generate this prediction, which is completely useless prediction for this block. Then the problem with PROF is that, so on the left side you see the normal operation of PROF when there is a small rotation, but when there is big rotation, this PROF tries to refine the sample values as shown in this figure B. In this case, you see that these refinement vectors, these blue vectors, are very big. So this, when they are very big, that gradient isn't valid. So this PROF not only doesn't improve the performance, also makes the prediction value very bad. So the method that we propose here is to fix this affine motion compensation and also PROF when there is large rotation. And the main idea here is that for the affine motion compensation part, so currently it gives this block, but if you notice that if we rotate each subblock according to the rotation, then we can get this block. So the idea here is very simple. So we just rotate subblock accordingly, and then we get perfect prediction block. For PROF, the idea is that currently there is this big motion vector refinement, this blue one. But our idea is that instead of refining this sample from this location, we can refine this sample from this location. So then this refinement motion vector will be small, and then that gradient can help here to improve the prediction. So in summary, the proposed method is like this. Here I compared the current method and the proposed method. So affine motion compensation has an initial step. So in initial step, it calculates some motion vectors based on the affine parameter, those corner motion vectors, and then does the motion compensation for each block, and then put all the sub-blocks together. But what we are proposing here is that changes are showed in block letter. So what we do here is that we first detect the large rotation, if there is any large rotation or flipping based on the affine parameters, then initialize parameters of PROF a bit differently, not that different. Then we do the normal job of affine motion compensation, and at the end we rotate subblocks. So there is not that big change. So for details, please see the paper. Here I'm not going to detail. But the important part is that how we detect this rotation, big rotation. So in the left figure, you see the current block. We define this AB and AC vectors, and also this 1, 1, 1 location. So based on affine parameter, we do the transformation. Then we see that how these vectors are changing. So for example, figure B is flipping. You see that the location of these vectors A prime, B prime, and C prime are changing. So if we calculate the outer product of these two vectors, we can detect that if there is a flipping or not. And for rotation, based on this example, we check where this 1 point maps in after affine motion transformation with respect to this corner. If based on its location, we can detect if there is around 0 degree or 90 degree, 180 degree or more rotation. So based on the values of this outer product and the location of this E point, we define 8 processing mode, which means that we detect no big rotation, 90 degree rotation, 180 rotation, 270 rotation, and also the combination of this with flipping, horizontal flipping, diagonal flipping, vertical flipping, and so on. So we detect this big rotation based on the affine parameters with these simple equations. Okay, so one of the use cases, as we said, is for this method is point cloud coding or video-based point cloud coding. Here is a short introduction about point cloud coding. So point cloud is a collection of pixels in the 3D space. So we have their location and their values, which is represented in 3D domain. There are different methods for point cloud compression. One of them is video-based point cloud compression, or VPCC, which is going to be finalized. The standard is going to be finalized soon. So this is our use case. How it works is that VPCC receives an point cloud, this input, tries to find some patches. So this is some surface of this object, and maps them to a 2D video like this. These are different parts of this input, and also their depths, and then feed this content to a video codec. This video codec can be anything. So VPCC is codec agnostic, so you can use HEVC or VVC or whatever. So here we have used VVC to code this content. So the point is that this content may have rotation in the object. So here in this example, you see that this is 2 different frames of this long dress test sequence. Here you see that this lady is packed here horizontally, but it is here vertically. So there is this 90-degree rotation and also flipping. So normal VVC cannot predict this one, but with our modification, we can do this prediction. So here are the results. We implemented the method in VTM7. We tested with natural content. So there is no loss, no gain. So we also expected that one. So because this modification, we have not designed it for natural content. We have designed it for a special content. So there is no loss, no gain. But we tested also in VVC, in VPCC use case. For this one, we had to modify the motion estimation in VTM to capture this 90-degree rotation. So we extracted some data, some metadata from VPCC codec and fed to the VVC or VTM. And with that one, we were able to do the motion compensation, motion estimation easier. Then here you see the result for random access case. The left one is the proposed method with that motion estimation modification. So there is in average 3% gain, or maximum this 7% gain. On the right side, you see the result only with modified motion estimation without proposed method. So you see that there is no gain. So difference of this table is the gain that proposed methods show. And here is a result for low delay B. That's also similar, 3% gain, maximum 7% gain roughly. And also this is without our proposed method. So this difference is the gain that our method shows. So as a conclusion is that we in this work we fixed PRAF and Affine for the case that there is large rotation. There is good gain for VPCC application, and the future study is that we try the same method for different content, like natural content. We try to modify the motion estimation for that we can have similar gain or part of the gain in natural content, or different types of content like cube map projection. There is also rotation. We try to test this method in that one. Okay, thank you very much. For any question, please contact my email address here.